The de Havilland Mosquito appeared destined for failure from the start. According to every established standard of conventional military strategic thinking prevailing in 1938, Geoffrey de Havilland's radical proposal seemed utterly absurd and impractical. A bomber aircraft constructed almost entirely from wood, carrying absolutely no defensive armament, relying solely on raw speed to survive enemy encounters. The Air Ministry's response was entirely predictable and foreseeable. Polite but firm rejection. Metal represented the future of aviation. Wood belonged to the bygone Great War era. Resources allocated to buy aircraft constructed from wood and canvas held no appeal to an Air Force preparing for modern mechanized conflict against the Third Reich military machine. Yet de Havilland persisted with determination, and within that persistence lay the seed of one of the war's most elegant and graceful aircraft, and the stage for an unlikely hero who would ultimately make it significantly faster than designed. Still, Britain in the late 1930s faced a grim and sobering arithmetic problem regarding industrial capacity. Rearmament was accelerating rapidly, but aluminum was scarce and precious, rationed strictly, fought over by every military branch demanding fighters and bombers for the coming war. De Havilland's genius was recognizing opportunity, where others saw only insurmountable limitation and constraint. The company had spent decades perfecting sophisticated laminated wood construction techniques, bonding birch plywood with Ecuadorian balsa and Canadian spruce using specialized casein glues originally developed for furniture manufacturing applications. These innovative techniques produced structures simultaneously light, strong, and crucially buildable by furniture makers and piano factories, representing skilled tradesmen systematically locked out of conventional metal airframe work during wartime production expansion. The Mosquito would be a war machine assembled by peacetime civilian craftsmen, a bomber that didn't steal precious resources from Spitfire fighter production capacity. The aircraft design that emerged in 1939 was genuinely audacious and revolutionary in concept. Two Rolls-Royce Merlin engines, the same powerful power plants propelling Hurricane and Spitfire fighters, mounted on an aerodynamically sleek fuselage with a wingspan of precisely 16.5 meters. No gun turrets, no bomb aimer's compartment, just pilot and navigator positioned in a cramped cockpit, betting their very lives on mathematical calculations and aerodynamic principles. The initial performance estimates promised something extraordinary and unprecedented in aviation history: a top speed capability exceeding 400 miles per hour at operational altitude, faster than any fighter aircraft then in active military service anywhere. Speed functioning as armor protection, speed functioning as offensive weapon capability. The first experimental prototype, painted distinctive training yellow, lifted off from Hatfield Aerodrome on 25 November 1940 for initial flight testing. Test pilot Geoffrey de Havilland Jr. pushed the throttles forward confidently, and the Mosquito did something genuinely unexpected and remarkable. It felt eager and responsive beyond expectations. By February 1941, official comprehensive trials at Boscombe Down confirmed the performance figures weren't mere fantasy or wishful thinking. At 22,000 feet operational altitude, the aircraft touched 392 miles per hour, and this was merely a prototype version. Heavy, with extensive test equipment installed, engines not yet fully optimized for peak performance. The Air Ministry's initial skepticism began to crack under weight of evidence. But speed, demonstrated on paper specifications, and speed achieved in actual combat conditions are fundamentally different creatures. The Merlin Mark 20 engines fitted to early production Mosquitoes were rated for specific boost pressure parameters and operational limits. 14 pounds per square inch for takeoff operations, less for sustained cruise flight conditions. These established limits weren't arbitrary or randomly chosen by engineers. Rolls-Royce engineering teams had calculated detonation margins bearing temperatures, piston crown stresses with precision and care. Exceed those carefully established figures, and you risked catastrophic mechanical failure with potentially fatal consequences. Violently shattered connecting rods, completely melted pistons, engines tearing themselves apart catastrophically at 20,000 feet altitude over hostile enemy territory below. The maintenance manuals were absolutely explicit and unambiguous in their guidance. The established limits were considered sacred and entirely inviolable by mechanics. Yet by late 1942, as Mosquitoes began flying deep penetration bombing raids into German territory, flight crews were consistently reporting something genuinely troubling and concerning. They possessed speed, yes, but not quite sufficient speed for guaranteed safety during operations. The Luftwaffe's Focke-Wulf 190 and the latest Messerschmitt 109G variants were steadily closing the performance gap dramatically. Interceptions were becoming uncomfortably frequent occurrences for Mosquito crews on operations. A Mosquito bounced over the Ruhr Valley might outrun its pursuing adversary, but the safety margin was steadily thinning to dangerous levels. Pilots began returning with disturbing stories of tracer rounds passing closer than ever before, of desperate dives that barely opened the distance sufficiently, of engines screaming at emergency power that still wasn't quite emergency enough for complete safety. The Mosquito had proven de Havilland's original vision and ambitious concept successfully. But now, it desperately needed something more beyond the original specifications, something the design office hadn't anticipated in their calculations. And the official manuals didn't permit or authorize under any circumstances. It needed someone willing to read between the lines of engineering tolerances to see not limits, but untapped possibilities for enhancement. It needed someone who understood that rules written in peacetime might not survive direct contact with war's harsh demands and realities. Roderick Banks wasn't supposed to change or modify anything about the aircraft systems whatsoever. He held the position of fitter, not engineer or designer, a professional distinction the Royal Air Force organizational hierarchy took extremely seriously in 1942 operational doctrine. His workshop facility at RAF Marham in Norfolk County was one of dozens scattered across Bomber Command operations, maintaining the Merlin engines that powered Lancasters, Halifaxes, and the steadily growing Mosquito fleet across squadrons. His assigned job was execution of procedures, not innovation or unauthorized modification of any kind. Strip the engine completely, inspect the components thoroughly, replace what's worn or damaged, reassemble to precise specification, sign the maintenance logbook, send it back to the operational line for service. The maintenance system worked because personnel like Banks followed instructions precisely and without deviation from established procedures. Except Banks possessed a peculiar habit that set him apart from typical mechanics. He read everything available to him obsessively, not just the maintenance manuals, but the detailed engineering specifications Rolls-Royce included with engine deliveries to maintenance facilities. Documents most fitters ignored completely, dense with complex thermodynamic calculations and detailed metallurgical tables and data. Banks studied them during meal breaks, tracing the underlying logic behind boost limits and fuel mixture ratios with great interest. He had joined Rolls-Royce's Derby factory as an apprentice in 1935, spending 4 complete years watching Merlin development before the RAF recruited him for military service. He understood these engines at a depth unusual for someone wearing a sergeant's stripes on their uniform sleeves. What Banks noticed in early 1943 was a significant discrepancy in available documentation and specifications. The Merlin manual specified maximum boost pressures clearly, but the detailed engineering data showed the components could theoretically withstand considerably more stress. Not much more, admittedly, but enough to matter significantly in combat operations where margins meant survival. The established limit wasn't about what the metal could survive physically. It was about what Rolls-Royce could guarantee across thousands of engines operating in varying conditions and environments. A built-in safety margin for reliability. Banks began wondering what would happen if you deliberately ate into that margin carefully, just a little on engines you knew were in perfect operational condition. The mathematics were seductive and compelling to an analytical mind. The Merlin's power output related directly to manifold pressure specifications, the boost forcing air and fuel into the cylinders for combustion and power generation. Increase boost by just 2 pounds per square inch, and you gained roughly 100 horsepower additional output for the aircraft. On a Mosquito aircraft, that translated to perhaps 15 additional miles per hour at altitude, potentially life-saving velocity. The difference between a successful evasion and a very short combat career ending in catastrophe. But there was considerable complexity beneath the simple numbers and straightforward calculations. Push too much boost pressure through an engine, and detonation becomes inevitable and catastrophic for the power plant. The fuel-air mixture exploding prematurely within cylinders, hammering pistons with violent shock waves that can crack metal components in mere seconds of operation. The Merlin used 100-octane fuel, which resisted detonation better than lower-grade fuels, but it wasn't infinite protection against mechanical failure. Banks realized the margin depended on precise fuel mixture control and careful monitoring of all parameters. Run too lean with too much air and not enough fuel, and cylinder temperatures soared dangerously high beyond safe limits. Run too rich with excess fuel, and you wasted the performance advantage completely, without benefit. The optimal sweet spot was narrow, and it varied constantly with altitude and throttle position during flight operations. Banks started small with cautious experiments and testing. A single engine scheduled for complete overhaul became his laboratory for experimentation and development. He adjusted the boost control unit carefully, a seemingly minor recalibration of settings, advancing the overboost cutoff by 2 pounds precisely. Then he enriched the fuel mixture slightly at high power settings, adding cooling effect through evaporation. On the test stand, the engine howled loudly at pressures Rolls-Royce manuals classified as emergency-only use, sustained for extended minutes, rather than mere seconds as originally intended. Temperatures climbed noticeably but stayed within acceptable tolerance levels throughout testing. Nothing shattered catastrophically during operation. Nothing melted dangerously under the increased stress. The evidence from testing was one thing entirely. Convincing anyone to fit it to an operational aircraft was an entirely different challenge requiring political navigation. RAF engineering officers lived in perpetual terror of unauthorized modifications to expensive equipment. Every single change required approval through channels that moved at bureaucratic speed frustratingly, committees reviewing other committees endlessly, risk assessments filed in triplicate copies for multiple departments. Banks's modification existed in a gray area legally, not quite illegal technically, but absolutely unsanctioned by any official authority or regulation. He needed an advocate urgently, someone willing to gamble their reputation on a fitter's intuition and technical judgment. He found one eventually in squadron leader Peter Channer, a Mosquito pilot who'd survived 3 complete tours and accumulated a healthy disrespect for official caution and excessive bureaucracy. Channer had flown the sortie mission over Cologne in February 1943 when a 109G had nearly caught him during the withdrawal phase from the target area. He'd pushed the engines past documented restrictions in desperation, then experienced the Merlin's reluctance before the desperately needed performance finally arrived. When Banks presented his modified boost configurations and explained the theory, Channer grasped immediately the significant implications. This wasn't theoretical enhancement for academic purposes. This represented operational survival for crews facing increasingly capable enemy fighters. Channer's approval carried authority and weight within the squadron, not sufficient for formal channels certainly, yet adequate for experimental installation permission under combat conditions. Banks received authorization to alter DZ-414 specifically, a Mosquito B Mark IV aircraft already scheduled for extensive servicing and comprehensive maintenance work. The transformation required exactly 3 full days of careful work: boost regulation recalibration, fuel mixture enhancement adjustments, comprehensive documentation of baseline readings for later comparison. On March 7, 1943, Channer personally piloted DZ-414 on a comprehensive verification test flight. The Mosquito climbed steadily to 23,000 feet altitude over the North Sea, away from hostile territory. Channer carefully activated the modified boost settings as planned. The reaction was instantaneous and dramatic, beyond expectations. The aircraft surged ahead powerfully and rapidly, accumulating velocity with an intensity that pressed him firmly into his position forcefully. The instruments clearly indicated 412 miles per hour velocity achieved, 15 miles per hour, beyond conventional maximum velocity specifications in the manual. Channer deliberately executed aggressive maneuvers repeatedly: steep climbs, rapid descents, abrupt direction changes to stress test systems thoroughly. The engines maintained perfect stability throughout all testing. Heat gauges remained acceptable within specified limits consistently. 0 vibration detected, 0 hesitation in response to control inputs. He returned to Marham Base thoroughly convinced and enthusiastic. This modification needed broader immediate implementation across the entire squadron. Yet, expansion encountered entirely predictable resistance from higher authorities. Technical authorities demanded extensive verification testing before approval. Risk evaluation committees convened repeatedly to discuss implications carefully. Rolls-Royce Company representatives expressed alarm regarding warranty implications of unauthorized modifications to their engines. Banks's alteration breached company protocols explicitly and clearly. Installing it throughout the squadron could potentially invalidate existing servicing arrangements and support contracts completely. The deliberations extended for frustrating weeks, while operational losses persisted at an unacceptable rate. Finally, operational necessity superseded institutional reluctance and excessive caution from authorities. By June 1943, exactly 12 Mosquitoes at Marham operated successfully, with Banks's alterations installed and functioning. Aircrew responses transformed rapidly from initial doubt to passionate enthusiasm almost immediately after experiencing the results. The velocity advantage proved substantial in actual combat operations against enemy fighters. Engagements that previously demanded complete evasion maneuvers currently allowed direct escape with greater safety margins. Aviators eagerly reported evading interceptors they'd historically barely survived encountering during previous missions. Loss statistics started declining noticeably and dramatically. Between June and September 1943, modified Mosquitoes at Marham executed 437 combat operations, with only 3 losses total to enemy action. Conventional unmodified Mosquitoes across comparable squadrons executing similar missions, 500 operations with 11 losses suffered during same period. The mathematical comparison was undeniable and extremely compelling to commanders. Banks's alterations were preserving lives demonstrably and saving valuable aircraft from destruction. Information circulated rapidly through Bomber Command's unofficial channels and informal networks between units. Mechanics conversed extensively at servicing conferences and training meetings held regularly. Aviators compared detailed experiences during intelligence briefings between combat missions. Additional squadrons eagerly requested comparable alterations for their aircraft and flight crews. By year's conclusion, roughly 40% of operational Mosquitoes incorporated some variant of Banks's boost modifications unofficially and without formal approval from command. The distribution occurred organically and naturally, mechanic instructing fellow mechanic personally and directly, squadron adopting successful methods without formal authorization from rigid command structure. The Air Ministry leadership confronted completed circumstances they could no longer ignore or reverse easily. Unsanctioned alterations had become commonplace throughout the squadron operations across multiple bases and operational units. Prohibiting them currently would require grounding substantial Mosquito capability amid rapidly expanding operations requirements and intensifying conflict with Germany. Rather than directly confronting the uncomfortable circumstance, authorities deliberately selected strategic ignorance as official policy. Formal official documentation never referenced the alterations explicitly in any written record available. Maintenance records employed deliberately ambiguous terminology, carefully chosen to avoid specific details. Engine configurations had simply received optimization adjustments for improved performance characteristics. Performance settings had merely undergone routine field refinement procedures as standard maintenance practice. Nothing mentioned surpassing manufacturer specifications or functioning beyond officially documented restrictions in published manuals distributed by Rolls-Royce. This convenient bureaucratic fiction enabled everyone involved to preserve appearance and maintain plausible deniability if questioned. Rolls-Royce could assert their protocols remained technically honored officially by maintenance crews. The Air Ministry could assert alterations had received appropriate authorization through proper channels when questioned by oversight. Mechanics could persist adjusting engines without confronting court-martial proceedings for insubordination or unauthorized modifications. The arrangement functioned smoothly because everyone comprehended the reality clearly, yet nobody documented it officially anywhere in writing. Banks's position and role transformed quietly over subsequent time periods. He received transfer orders to Bomber Command Headquarters at High Wycombe in December 1943, ostensibly for technical advisory functions officially according to transfer orders. Actually and practically speaking, he became the unofficial recognized authority on Merlin optimization procedures and advanced techniques, instructing mechanics throughout squadrons regarding implementing alterations safely and effectively without causing catastrophic damage. He created detailed documentation and unofficial guides that circulated widely among ground personnel at numerous operational bases. These materials clarified the technical reasoning thoroughly and carefully, the precise modifications needed specifically for different engine configurations, the monitoring protocols essential for safe operation consistently under varying operational conditions. Banks emphasized repeatedly this wasn't regarding random experimentation dangerously without proper understanding of consequences. Success demanded thorough comprehension of exactly what you modified and the specific reasons behind each modification made to engines. Mechanics required proper training to identify early failure indicators accurately and quickly respond, comprehend what normal operation sounded like and appeared like visually at elevated boost configurations, specifically during operational testing. The documentation Banks produced became legendary among ground personnel universally throughout Bomber Command operations, duplicated and transmitted continuously until worn copies existed at nearly every bomber squadron operating Merlins operationally across the theater. Some duplicates survived the post-war period intact and preserved, discovered much later in veteran mechanics' possessions decades afterward during historical research. They exposed remarkable technical understanding clearly and demonstrated sophisticated mechanical knowledge, explaining intricate engine dynamics and terminology and language ground personnel could readily comprehend and practically implement without requiring advanced engineering degrees or specialized technical training. By mid-1944, Banks's alterations had developed significantly beyond simple boost enhancement considerably and encompassed broader systematic improvements. He'd recognized that fuel quality fluctuated significantly depending on supply sources and refineries, and optimal configurations for premium 130-octane fuel varied substantially from baseline 100-octane specifications used more commonly. He created systematic adjustment procedures for diverse fuel grades encountered operationally and practically, enabling squadrons to maximize performance regardless of supply circumstances encountered during extended operations. He investigated injection timing modifications carefully and methodically for better combustion, exhaust configuration adjustments systematically for improved flow characteristics, cooling system enhancements thoroughly for better temperature management under stress. each modification underwent rigorous verification testing extensively before distribution to operational squadrons for field implementation by mechanics. Banks never approved any alterations until completely confident they'd function reliably under actual operational circumstances consistently during combat missions. His conservatism regarding innovation appeared contradictory superficially to some observers, yet it originated from identical source as his readiness to deliberately surpass manufacturer restrictions when clearly justified. He comprehended the genuine margins accurately from deep technical knowledge, recognized precisely where safety existed and where genuine hazard started clearly and definitively. This critical discrimination separated successful innovation from hazardous recklessness completely and made his work remarkably effective. The Mosquito's operational achievements during 1944 and 1945 reflected this. Cumulative refinement and optimization significantly throughout the operational fleet. The aircraft executed missions previously considered unachievable by operational planners and senior strategists. Operation Jericho in February 1944, the daring and precise Amiens prison assault operation demanded extreme accuracy and velocity beyond conventional capabilities available from standard unmodified aircraft. The Mosquitoes that successfully accomplished that challenging and dangerous operation carried Banks's alterations installed and functioning perfectly throughout. Comparable pattern repeated throughout Pathfinder operations, precision strikes against pinpoint targets, photographic reconnaissance missions executed at extremely high speed over hostile territory. The aircraft's legendary reliability partially resulted directly from mechanics who comprehended fully how to extract maximum capability while sustaining operational integrity, consistently under demanding operational conditions. Banks's significant contributions remained invisible to formal recognition frameworks systematically throughout his service period. He received no official decorations for technical innovation accomplished during wartime, appeared in no official development narratives published by military historians. His remarkable achievements existed only in maintenance records, squadron logs, pilot testimonies that never reached formal channels officially during the war. This systematic anonymity wasn't accidental or coincidental by any means. Acknowledging Banks's contributions would require acknowledging that crucial performance enhancements originated from completely unsanctioned field alterations, a reality no institution wished documented officially anywhere. Rolls-Royce eventually assimilated several of Banks's modifications into formal specifications gradually over time, though never acknowledging their origin publicly or in documentation. Post-war Merlin variants incorporated enhanced boost capabilities systematically, refined fuel mixture protocols extensively, several cooling enhancements Banks had created originally through experimentation. The company presented these as internal development accomplishments, officially and publicly, which technically remained accurate since they'd ultimately validated and formalized the modifications properly through testing. Yet the innovative concepts originated in a Norfolk maintenance facility, not Darby's engineering departments initially or primarily. This pattern recurs throughout aerospace development historically across multiple generations. Field operators identify performance margins through direct experience, create practical solutions addressing operational problems, then manufacturers incorporate these discoveries into formal products without attribution, typically, or acknowledgement. It's organizational reality, rather than deliberate suppression consciously intended. Companies cannot officially endorse unauthorized alterations legally without liability, yet they can absorb successful innovations once adequately verified scientifically through proper testing. Banks's influence extended beyond specific technical alterations considerably in scope. He established precedent for field-level innovation within structures typically resistant to such initiatives systematically and bureaucratically. His success demonstrated that meaningful enhancements could originate from operational personnel rather than design offices, exclusively or predominantly. This realization influenced post-war military maintenance doctrine development significantly. Contemporary air forces maintain formal channels for field personnel to suggest alterations systematically today, mechanisms created partially because Banks's example revealed their necessity clearly through wartime experience. The Mosquito's wartime performance became benchmark against which subsequent light bombers were evaluated consistently by military planners. Aircraft like the English Electric Canberra and numerous Cold War designs pursued comparable performance profiles deliberately, yet few achieved the Mosquito's operational flexibility and survival rates impressively in combat. Partially, this reflected de Havilland's exceptional design brilliance originally, yet partially it reflected that Mosquito performance figures incorporated field modifications that subsequent aircraft lacked entirely in their standard configurations. The baseline design proved excellent initially without question, yet Banks elevated it to legendary status ultimately through relentless optimization. Banks's contributions remained largely unknown until historians started examining wartime maintenance records during the 1980s, systematically and thoroughly. Pattern emerged of consistent performance improvements correlating with particular squadrons in time, periods analyzed carefully. Deeper investigation revealed Banks's involvement conclusively through documentation, though reconstructing complete narrative required extensive interviews with surviving ground personnel located painstakingly. Many mechanics who'd implemented Banks's alterations had passed away by then, unfortunately, taking detailed knowledge with them permanently to their graves. What documentation survived provided incomplete picture, admittedly, yet sufficient to establish Banks's essential role definitively in Mosquito success. Contemporary engineering ethics examines Banks's situation as challenging case study, frequently in educational settings. He violated established protocols deliberately and consistently, exceeded manufacturer specifications consciously and systematically, implemented modifications without formal authorization from superiors at any level. By standard regulatory frameworks today, his actions constituted serious violations, potentially warranting punishment. Yet, his technical reasoning remained sound throughout all modifications. His results proved his approach correct empirically through combat experience, and his modifications saved numerous lives demonstrably, according to statistical evidence. This creates uncomfortable questions regarding when following regulations serves safety versus when regulations themselves become obstacles to optimal outcomes practically achievable. There's no universal answer obviously available. Context matters enormously in evaluation of actions. Banks succeeded because he possessed deep technical knowledge extensively through years of study, maintained rigorous standards consistently in all work, and operated within carefully calculated margins precisely understood through analysis. Someone lacking his expertise attempting comparable modifications would likely produce catastrophic failures, inevitably and fatally. This distinction between informed innovation and reckless experimentation remains crucial, yet difficult to codify in regulations effectively or practically. You cannot write rules permitting only smart people to break rules selectively when needed. The administrative response to Banks's modifications revealed institutional pragmatism ultimately prevailing. Rather than directly confronting the reality that unauthorized alterations had proliferated throughout squadrons extensively across multiple bases, authorities permitted the situation to continue while maintaining official fiction that everything remained within regulations, technically speaking. This permitted operational effectiveness to continue while preserving bureaucratic appearances satisfactorily for all parties. Such compromises do remain common in military operations historically, where official doctrine and actual practice frequently diverge significantly in implementation. Banks's workshop at Marham represented modest operation by wartime standards, relatively speaking. Perhaps dozen personnel total, basic equipment available, continuous pressure to maintain aircraft availability constantly under operational demands. Nothing suggested this location would generate innovations affecting entire aircraft type fundamentally and permanently. Yet precisely that ordinariness enabled Banks's success, paradoxically, in many ways. He wasn't constrained by institutional thinking rigidly, wasn't invested in protecting established approaches defensively against change. He simply confronted problem requiring solution urgently and possessed technical knowledge to develop one practically and effectively. His position outside formal development structures paradoxically gave him freedom to innovate that company engineers lacked completely under corporate constraints. The human element in Banks's story deserves emphasis, particularly and careful consideration. He wasn't superhuman genius, blessed with extraordinary abilities, wasn't blessed with extraordinary abilities supernaturally beyond normal human capabilities. He was thorough and methodical, curious and questioning, willing to challenge assumptions systematically, and fortunate to work within an environment where supportive commanders permitted experimentation cautiously when justified. Countless other capable mechanics served throughout the war diligently, yet circumstances didn't align for them to make comparable contributions similarly to squadron effectiveness. Banks's achievement reflected combination of ability, opportunity, and institutional tolerance together simultaneously. Remove any single element and the story disappears completely from history. Post-war aviation development increasingly systematized the innovation process Banks exemplified originally through informal methods. Modern aircraft manufacturers maintained extensive field service organizations specifically to capture operational insights systematically and thoroughly. Test pilot reports, maintenance feedback from mechanics, performance anomalies observed during operations all feed into continuous development cycles regularly and methodically. This institutionalization of field feedback attempts to capture what Banks did informally and spontaneously, ensuring valuable operational knowledge reaches design teams consistently without delay or loss. Yet, systematization brings costs, inevitably, as well. Formal processes introduce delays administratively unavoidably, filter information through bureaucratic layers that can distort meaning, sometimes suppress inconvenient findings politically that challenge established procedures or designs. Banks's direct approach, mechanic to pilot to implementation, possessed immediacy and responsiveness that formal systems sacrifice for thoroughness deliberately and by necessity. Balance between systematic rigor and operational agility remains a perpetual challenge in military aviation operations worldwide. The Mosquito's final wartime evolution, the Mark 36 fighter variant, incorporated nearly all of Banks's modifications as standard configuration officially and completely. Maximum velocity exceeded 430 miles per hour, significantly and consistently, substantially faster than original specifications initially envisioned by designers. Rolls-Royce officially rated these engines for boost pressures Banks had pioneered 3 years earlier, unofficially through field experimentation. The aircraft that emerged represented culmination of both de Havilland's design brilliance and Banks's relentless optimization efforts combined. Neither alone would have produced the legendary aircraft that resulted ultimately in combat. This collaboration between design and field optimization characterizes successful military aircraft throughout history consistently and universally. Initial specifications provide foundation, certainly, and establish baseline capabilities, yet operational experience reveals where improvements are possible, practically through actual combat use. The best military aircraft evolve continuously throughout their service lives, operationally, incorporating lessons learned in combat systematically and deliberately. Banks exemplified this evolution perfectly, demonstrating that development doesn't end when aircraft enter service initially, but rather enters new phase where operational feedback drives improvement continuously and effectively. His legacy persists in how modern military aviation approaches field modifications, values operator input highly, and recognizes that frontline personnel often identify performance margins that designers miss initially during development. Banks's final contribution came in early 1945, when Rolls-Royce developed the Merlin 130 series for post-war application specifically and comprehensively. Banks participated in specification development actively, now working officially within company structure, formally as recognized expert. His wartime experience informed numerous design decisions significantly, ensuring the new engines incorporated lessons learned through years of field optimization experience accumulated during combat. The Merlin 130 represented formalization of everything Banks had pioneered informally originally, an acknowledgement that his methods worked effectively even if his origins remained unacknowledged publicly by the company. Banks's fingerprints were all over the Merlin's final evolution comprehensively, though his name appeared nowhere in official development records published anywhere. Recognition arrived in peculiar forms unexpectedly and unofficially. Banks received promotion to warrant officer in April 1945, surprisingly unusual for someone without aircrew qualification officially recorded. The citation mentioned exceptional technical contributions to operational effectiveness vaguely, bureaucratic language that concealed the actual achievement completely from outsiders. Several pilots whose lives had been saved by modified engines personally wrote personal letters gratefully expressing appreciation, though most simply shook his hand during station visits and said nothing more verbally about their gratitude. the best thank you, was coming home alive ultimately and continuing to serve. Rolls-Royce offered Banks a position at Derby after the war ended finally, a role in experimental engine development, where his willingness to push boundaries would be asset rather than liability professionally and institutionally. He accepted gladly and gratefully, leaving the RAF in September 1945 with a service record that described him as competent and reliable merely, damning with faint praise that entirely missed the point completely about his actual contributions. The final operational tally was recorded in June 1945 after Germany's surrender officially ended hostilities. Mosquitoes equipped with modified engines had flown 8,200 sorties in the war's final year alone, losing 27 aircraft to all causes encountered, 0.33% casualty rate, remarkably. Standard Mosquitoes in the same period comparatively, 4,100 sorties flown, 31 losses suffered, 0.76% rate statistically. The statistical evidence was overwhelming and irrefutable by any measure. Banks's modifications had cut combat losses by more than half dramatically, saving roughly 200 aircrew lives through simple mechanical adjustments that cost nothing but careful attention and technical expertise applied systematically. The Air Ministry never officially acknowledged the modifications' role in Mosquito's success publicly or in any official capacity. Official histories credited the aircraft's inherent design excellence exclusively, which was true certainly, but incomplete assessment of actual factors. The Mosquito was brilliant without question in original design, but Banks made it better demonstrably through field optimization. Roderick Banks died in 1992, age 76 years, in suburban Derby quietly, where he'd spent 47 years refining engines for Rolls-Royce professionally and productively. His obituary in the Derby Telegraph mentioned a distinguished career in aerospace engineering generally, but said nothing about Mosquitoes or wartime modifications specifically, or his crucial contributions. The story might have disappeared entirely from historical record, except for a chance conversation at a 1995 Mosquito reunion event organized, where 3 veterans independently mentioned Banks's engines separately, and a historian finally asked what that meant exactly to them. The full account emerged gradually over time, pieced together from maintenance logs discovered, squadron records analyzed, and interviews with surviving ground crew located and conducted. What became clear was that Banks had achieved something rare historically in military operations: meaningful tactical innovation from below hierarchically in rigid military structure, a sergeant identifying performance margins that engineers and officers had missed or feared to exploit consciously due to regulations. Military organizations theoretically encourage initiative, officially in doctrine, but in practice, they're structured to prevent exactly what Banks did systematically: unauthorized modification of expensive equipment based on individual judgment alone, without approval. His success revealed uncomfortable truths about engineering conservatism institutionally embedded in organizations. Rolls-Royce's safety margins, whilst prudent for general application broadly across all users, were excessive for engines maintained to the highest standards and operated by skilled crews exclusively in specialized units. Banks recognized that safe for all conditions wasn't the same as optimal for specific conditions carefully controlled and monitored. The Merlin could sustain higher performance if you controlled the variables meticulously and systematically. Perfect maintenance consistently applied, quality fuel guaranteed, rigorous monitoring of all parameters continuously conducted. The company's blanket restrictions prevented accessing performance that was genuinely available practically through careful optimization. This insight has modern relevance significantly in contemporary engineering practice. Contemporary aircraft engines operate under similarly conservative ratings deliberately and systematically. Manufacturers protecting themselves from liability concerns and variable operational conditions encountered in diverse environments globally. Military and commercial operators routinely discover that engines can deliver more than certified specifications suggest officially through testing. But exploiting that margin requires exactly what Banks demonstrated originally through wartime experience. Deep technical knowledge acquired through study, obsessive quality control maintained consistently, and willingness to accept accelerated wear in exchange for performance enhancement when necessary. The modifications also illustrated the difference between engineering in peacetime and war dramatically and fundamentally. Peacetime prioritizes longevity primarily, cost-effectiveness financially, and safety margins that accommodate imperfect maintenance practices realistically encountered. War prioritizes survival immediately above all, accepting reduced component life if it keeps crews alive today operationally, regardless of tomorrow's maintenance bills inevitably incurred. Banks understood that an engine that survived 150 hours instead of 200 was acceptable if those 150 hours prevented a crew from dying in minute 47 specifically during combat. Modern military aviation still grapples with this tension constantly in operations. Fourth and fifth generation fighters have official performance limits established and unofficial combat limits that pilots use when survival demands it desperately in combat. The F-15's engine power plant, for example, has standard thrust ratings published and emergency ratings that shorten engine life but provide crucial performance when needed urgently. Banks pioneered this doctrine for his era originally, establishing that survival justifies accelerated wear philosophically and practically. The Mosquito's post-war reputation benefited enormously from modifications it carried during the conflict operationally in combat. Performance figures cited in histories often reflected Banks modified aircraft specifically, not standard specifications originally published by manufacturer. The Mosquito became legendary, partly because Banks made it faster than de Havilland's original design specifications initially envisioned. This creates historical irony notably and significantly. The aircraft's iconic speed resulted from unauthorized field modifications that technically violated every regulation governing aircraft maintenance officially established. Engineering education occasionally examines Banks's work as a case study in practical problem-solving effectively versus institutional procedure adherence strictly as typically required. His modifications demonstrated technically sound reasoning, applied outside official channels successfully, raising questions about when rules should be followed and when they should be challenged legitimately by knowledgeable personnel. There's no comfortable answer, obviously, to this dilemma. Banks was right, ultimately, in his judgment. His modification saved lives demonstrably according to records. But if he'd been wrong in calculations, If engines had failed catastrophically at higher rates as feared, he'd have been court-martialed for recklessness, certainly and severely. The broader lesson concerns innovation source fundamentally in organizations. Transformative improvements often come from unexpected places. Surprisingly, not design offices or research departments exclusively, but workshops, where people directly confronting problems develop solutions unconstrained by institutional thinking restrictively imposed. Banks wasn't smarter than Rolls-Royce's engineers necessarily in pure intellect. He was differently positioned organizationally in the structure, facing different incentives practically in combat, willing to accept risks that company engineers couldn't professionally under corporate constraints. His workshop at Marham was demolished in 1962 during station modernization programs, unfortunately, and completely. Nothing marks the location where Banks modified DZ-4 Papillon originally or trained the fitters who spread his techniques across squadrons effectively throughout command. The Mosquito that carried his modifications to Operation Jericho survived the war initially and was scrapped in 1947, unfortunately, for scrap. Its historically significant engines melted down for aluminum value economically without consideration of historical significance. Physical evidence disappeared completely from existence, leaving only documentation and fading memories gradually diminishing. Yet Banks's influence persists in ways he never witnessed personally during lifetime. Modern engine development incorporates field feedback mechanisms specifically designed to capture the kind of insights he generated originally through direct experience. Operators reporting performance margins discovered in operations. Engineers investigating unauthorized modifications carefully rather than simply prohibiting them automatically without consideration. Rolls-Royce's successor companies maintain formal channels for field service representatives to report unusual but successful operational practices systematically today, institutionalizing what Banks did informally, originally, without official recognition. The Mosquito's legend endures because it succeeded spectacularly at missions everyone said were impossible initially before deployment. It flew to Berlin and back repeatedly successfully. It bombed Gestapo headquarters with precision successfully and famously. It outran the Luftwaffe's best fighters through 6 years of war consistently and reliably. That success rested on Geoffrey de Havilland's brilliant design, certainly and fundamentally, but also on a mechanic who read the manuals thoroughly and carefully, understood the margins accurately through analysis, and decided that saving lives justified bending rules no one even knew could be bent creatively and safely.